So I am still in the process of grading your exams. I will post the grades online as soon as they are done. And then you'll be able to, and then I will return the exams to you. It's possible, depending on if we find there's a question that was a complete bomb, then basically then there'll be a chance to make up that question in labs or something like that. So, but again, that'll be adjusted. I think I've got everything but for. I think basically what I need to still grade are the two functions that you had to write, plus the 2 pages before that. So not too much more. It's a lot of work grading 180 exams, and my TAs were all very busy. So, busy in the sense that they left it all for me. So, anyway, so your latest homework will deal with slices. So, a lot of the next few weeks will be dealing with manipulating text in some way, shape, or form, whether it being slicing, dicing, or arranging text, or reading text from a file, or searching text. Pretty much most of the rest of the semester will be dealing with how do we work with text, right? Now that we've done a lot of what we had to do, it's pretty much straightforward for text. So today we're going to learn about the history of a bit of a history of computing in terms of doing cryptography. Now, I'd love it if you could work along with me on this one. To find this, you can just go to the Foundations of Python Programming over here, right into our book for our textbook, and click on project number 9. So we'll be, and I will be reading through the comments you left. I did see one and said, hey, would like more project-based homeworks. And don't worry, pretty much all the homeworks from now on are going to be like project-based. This one's the Pig Latin's a fairly simple project-based one, but like pretty much everything over here from now on is less make work and more actual do something with a purpose. So, and pretty much all the examples in class will be do something with a purpose now. So here, substitution ciphers. So ciphers, codes, ciphertext, plain text, encryption, decryption, cryptanalysis, cryptography. What the heck do they all mean? And why do they sound like they've been made by a vampire? Crypts? What are we talking about here? So all right, encryption and decryption. These are the acts of basically making things unreadable and readable for an intended recipient, right? The goal of encryption and decryption is to basically make it so that I can send you a message and you can receive it, but there's not going to be but nobody else can read it. Okay, that is the goal. I can send it to you. Somebody intercepts it. They can read it, but they can't decipher it. Is more the thing. Even if they get their hands on it, they can't decipher it. So I send it unintelligible to them. That's the purpose of encryption, of doing encryption. Cryptography is the act of making various encryption algorithms. That's the study of basically doing things. Of making ciphers. That's the word I'm looking for, because there's a very distinct definition between ciphers and codes. A code is basically saying something like this. Hey, did you deliver the package to Vinny? Yeah, I delivered the package to Vinny. He's going to be sleeping with the fishes tonight, right? Using English, using coded language, using subtext, using, sort of all sorts of coded language, right? Where basically it's intelligible, but words have different meanings. Package being bomb, sleeping with the fishes, dead, right? So, those are the kind of, that's a very classic, mob movie kind of message. Ciphertext, on the other hand, is something like this. BKF Gam Dazje. Right? That's ciphertext. Decodable by using pen and paper and a lot of trial and error. So a bit of history on encryption and decryption and that kind of stuff. The the earliest type of encryption, I think, was fairly early on, like around the zeros. So I can't remember if it's plus or minus 300 there. I think it was closer to the minus 300 BCE. 300 BCE. And the top of the technology was something called the Caesarean cipher. Now, the Caesarean cipher, it basically is from, as you might guess, Rome, named after Caesar. The idea here, and I don't think it was probably not 300 BCE, but we're getting pretty close to like year zero there. The idea here is that I've got this nice big empire, and I need to send these orders to generals throughout the world. Roman Empire. Let's just take a look at the Roman Empire or Roman Republic. Post-Republican period, right? The Roman Republic became the Roman Empire. It actually got so big that you got two emperors at some point managing it. And you might say, and to the point that basically, yeah, people talk about the fall of the Roman Empire when Rome actually fell in 1440s. The eastern half of it did. In Greece. Modern day Turkey. So the Roman Empire, as you can see, this is kind of the furthest extent, the greatest extent, 117. Pretty big country there, right? It's even made all of its way to Britannia. So, pretty big, required, you had two people ruling from it at some point, which was you had somebody in Rome and somebody in Constantinople. Now Istanbul, but that's nobody's business but the Turks. So, anyway, so this is a big empire, big military conquests, right? And the issue is you annex some territory from these raiding barbarians, and lo and behold, these new citizens who are now paying taxes would like you to defend them from the other raiding barbarians. So you have to go out and annex some more territory. So this requires a constant amount of generals being sent messages. Now, mind you, having to send messages wasn't necessary, and like code messages and hide them wasn't necessarily the biggest thing, I guess, of importance early on, because people really couldn't read back then too much, right? Literacy wasn't necessarily something you strived towards. But generals are expected to read orders and write orders, and you might think, well, if these guys intercept my orders and maybe they have somebody among them who could read, they could totally read that we're gonna attack them, like go to these positions here, and they could totally just outflank us and kill us all. That seems like a very bad proposition. So the idea here is that we're going to keep the barbarians who might be able to read Latin. By the way, aside here, barbarian. Anybody know where that comes from? Barbarian. Uncivilized or primitive generalization comes from the Greek barbaroi. In ancient Greece, the Greeks used the term to describe those who did not speak Greek and follow classical Greek customs. In other words, the Greeks were like, well, anybody who's a barbarian, just kind of sounds like they're saying barbar to us, right? Because they don't speak Greek. So there's a lot of things but anyway, barbarians in this case basically in this meaning people who are not Roman and don't speak Latin in this case. So anyway, gotta send these messages, want to encrypt them. So the easiest way is that we're going to use something called the Caesarean cipher, which is fairly simple. What we're going to do is that we are going to take our message and substitute all of our letters in a specific manner. Actually, easier to show you on text. Why am I doing this over here? So, Guinea, right? Let me go ahead and write the alphabet for you guys. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. Let's go and say this is in, and out is this. And the idea with this is that will code our message like so. We'll take our encryption, and the out will be like this. All I did was take the first 3 letters and move them to the back, and what that did is now I've essentially turned my alphabet into D, E, F, G, H, I, all the way to ABC, right? 16, still got 26 letters here. But the idea here is if I want to send a message, and just like programming languages have Hello World, cryptography has its own version of Hello World, which is attack at dawn, which kind of goes back to the whole military aspects of cryptography. Attack at dawn, which will be translated, well, A goes to D, T goes to W, A goes to D, C goes to F, okay? Right, and notice that all we're doing here is we're moving each letter 3 up in the alphabet, right? T, the letter 3 after T is W, 1, 2, 3. K, 1, 2, 3, that's N, so notice K and N. So N, so DW, and then we see a D here, so that D is G, D, W is Z, and then N is Q. Okay, and if I wanted to be sure it was harder to crack, I might decide to remove all the spaces and the exclamation points, right? And then break it up into 5s, so that's easier for the person receiving to decrypt it. Okay, that's typically the way it works. And so I, Caesar, will send this message out encoded to my generals. Then my general received this. He won't get this bit. He's going to get this. But he knows about the Caesarian cipher. Barbarian intercepts the message, kills the messenger. He's got a bunch of gibberish. Because barbarians, very few of them can read, and those that probably do don't probably know about the Caesarian cipher. Now, the Caesarian cipher, again, is what we call substitution cipher. What we were doing is that we were substituting all A's with a D, all B's with an E, all C's with an F, and so on. We were substituting each letter with another letter. This is the classic way of basically creating a cipher. So to translate it, I know that basically a D, I have to move 3 letters back, so that's an A. W goes to T, right? I go from out to in this time around. D goes to A, and then K at D-A-W-N, right? And so I've got this string of letters, atakata. So even if you're, and notice that if you're trying to just break this normally, it's not like 5-letter word, 5-letter word, no, it's not 5-letter word. And then I just combine it all together and then try to piece it together from there and hope there's nothing too ambiguous. So attack at dawn, right? Which is pretty useless considering the message probably took a couple of weeks to get to me. So anyway, this was the height of basically encryption for a while until we hit the Civil War, which was the Vignere cipher, which the way that would work is that basically the issue with this is that it takes basically there's only 26 possible combinations as there are here right now. And the Vignere cipher basically said, well, maybe we'll move every 5 letters, we'll do the first letter 3 letters, the second letter 4, the fifth letter 5, the third letter 5, 6, the fourth letter 6, and the fifth 7 letters, and then we're just going to move on, and we're going to repeat that pattern every 5 letters. We're not going to get into that right now, but suffice to say this works for right now. Now, the issue with substitution ciphers is that they've really, a Caesarian cipher only has 26 possible combinations. But, and we're going to explore that. So here is a picture from a German museum. This is an Enigma machine, right? This is basically the encryption decryption operations are difficult, so put them into some kind of machine for a specific task and let them do that. Notice you've got these reels and it's running, and what it's going to do is run it through multiple substitutions, and then every time they hit a letter, these move, so they change, so the encryption change, making it very, very hard to crack. So what you need is to have the appropriate amount of wheels and have them in the appropriate, or rotors rather, and have them in the right order, in the right starting order, which is what you would keep in a book. Those were what we would call the key, right? So you would put P and it would output B, right? Is the idea here. The Enigma machine was used by the Germans during World War II to encrypt orders for the movements of troops and German U-boats. Alan Turing worked in England, and he built the Bombe, one of the first computers that decrypted messages that were encrypted by Enigma. So we talked about that previously. So let's take a look at this secret message. Now, typically when we're given a secret message like this, there's typically like a hint in the page somewhere what the message is. And it says you might type in the letter P, and the output would be B. Okay, that seems like a pretty good hint. So let's go over here and adjust that. So you might put in the letter P and you get out B. So let's line that up. So let's see. So best way to do that is, yep, I'll just simply delete, add into here. So P over here, right? Because right now if they're saying we can solve it by hand, then it's probably something pretty simple. So so A, B, C, D. So, right, it said P, and all I'm going to do is I'm going to assume it's a Caesar cipher over here, okay? All right, so they said P, given a P, you get B. So B, C, D, F, G. So right now I'm just creating the rest of that cipher. H, I, and so from J to Z is the rest. Everybody kind of understanding how I'm doing this or completely lost? Here we go. Right? No, that's not right. A, B, C, right, because they said P is B, right? So we want P and B to line up. There we go, right? P and B to line up. And then I, J, K, L. There we go. So it's just a matter of getting it into the right formation like that. It's just some text manipulation on my part. But assuming it's a Caesar cipher, right? And they're probably going to, if it's the first assignment, probably going to do a Caesar cipher. And this is the kind of stuff that you use when you break codes, like stuff like that. So, let's see. So the message is this. And, oh, I think there's some hints down here, right? It says, right, drag the, oh, right, let me reset this, right? I worked through this before. So the encrypted Enigma is much more sophisticated than the previous question. Secret message has a simple substitution cipher. I've given you one hint. Let's see. Check me. I'll put something in. Try again. A equals O. A is O. So that seems to work out with our B and P, with our P giving P. Right? Remember, we're going from out to in. So A going to O works with our P going to B there. Because P going to B is in to out, from plain text to ciphertext, as we call it. And here it's saying that the A in the ciphertext is an O in the plain text. Plain text being the plain stuff you can read, ciphertext being the scrambled stuff. So let's go ahead and assume this is right and decrypt it by hand for right now. Okay, so B is P, right? And we're working from out to in. K is Y. F is T. G. Yeah, where's G? G is A, B, C, D, E, F. Oh, G. Did I mess up somewhere? A, B, C, D, E, F, G. E, F, G, H, I, J, K, L. E K Y T to 8 Q R S T U V W A. Yeah, I seem to have messed up somewhere, I think, because I know what the message is. It's fairly straightforward. But let's keep going. U, G to U, A to A is O, M, A, D to D is to what? D is R, O, Z is L, Z is N, J is X, and E is S. So I would suffice to say that basically everything from here down seems to be working, but I seem to have messed up my whatever I lined up. Let's see. So this is why encrypting from my hand is stuff. But let's see. So B, we know that A goes that A and O are the same thing. We know that K and P are the same. Sorry, P and B are the same thing. So K and T. Let's see if that's check me. 2 out of 2 incorrect. So other way around. So Y has to be K. Okay, Y has to be K and T has to go to F. So T here has to line up with F. So insert T, and what was the other one? K has to line up with Y, which it does. J, K, L, M, N, O, P, Q, R. So what did I mess up there? Or do I just need to do it like this? A, B, C, D, E, F, G. Or do I just have to do it the other way around? Sorry, people. Okay. And then O, P, Q, R, S, T, U, V, W, X, Y, Z, A, B, C, D, E, F, G, J, K, L, M, N. That's right. Because G should go to okay. Because I know what the answer is. Because I solved it this morning. Because I solved it this morning. I'm like, why? Because I know, because the way I knew, by the way, is that it was PYT, and I'm like, it's a Python class. They're spelling Python rocks, aren't they? Right, is the thing. And I'm not sure where I'm lining it up wrong, so if you can figure that out, please let me know. Yes?
You lined up the cipher to the normal one instead of the normal to the cipher. And then the cipher alphabet.
So
you had Y going to K instead of K going to Y, for example.
Y going to K. So let's go back to here for a second. So I have Y going to K instead of K going to. So what do I need to adjust then?
Yeah, so the top line.
Mm-hmm.
So if you go like where B is P, right?
Yep.
So take the B on the top line and line up with P on the bottom line.
The B on the top line and line up with P?
Yeah, B, so it should start OPQ. The out should start OPQ.
Ah.
You just line them up backwards.
Like so? Oh. Yeah, so... Yep. So let's see. G now goes to... It's still wrong, I think.
You have
Two
two T's.
T's? QR... QRST. Well, there you go. That was probably a huge issue there. All right. So, yeah. Suffice to say, doing this is hard, which is why we make computers do it. So how do we make computers do this? So actually most of the time we didn't have a computer to do this. We had a nice little device like this so that you wouldn't mess up like I did with maybe putting in two T's. So all it does is simply shift a certain number. So shifting 5 turns A into F, and if you go back past the end of the alphabet, you just simply start over again in the alphabet, which means basically that you got to use modular arithmetic for the computer to do it. Typically, what you do is the Caesar cipher, and you just line up like this. So say we wanted to encrypt the quick bound fox jumps over the lazy dog by rotating it forward 13. This is actually pretty popular, ROT13 it's called. Basically the idea here is that we'll disguise it by basically going to a letter 13 after the current letter. So now to go back into something that we talked about very, very briefly, but now it's going to become relevant. So each string in Python has a value. So we can figure out that value by going to by saying ORD. So A has an ASCII value or a Unicode value of 97. Capital A has a value of 65, right? And notice that basically that B, 66, C is 67. Why am I doing this? I should probably write a for loop, right? For I in, so for, let's say, I in range 66, let's go from 65 to 128. Print I, comma, CHR I. CHR is the reverse of ORD. It takes a letter, it takes a number and converts it into the appropriate ASCII value. So if we look at this chart, right, 65 becomes A, 66 is B. So if I were to choose D of 68, I'd get ORD of D, I'd get 68. If I were to do ORD of the caret symbol, I'd get 94. Right, and we can just try that to confirm. ORD caret, which is not nearly as tasty as the real things. So ORD caret gives us 94, right? And then if we were to take CHR of 94, that swaps it back to caret. So this is pretty cool because this means that basically if I want to take A and get the letter 3 after it, well, I can't do that. But what I can do is it looks a bit complicated, but it's not nearly as complicated as it seems. Oh, right, forget. ORD A plus 3, lowercase a plus 3 gives me 100. And then take that value and turn it into, and then CHR that entire thing. So convert this into a number, add 3 to it, and then throw it into character, into the character function, which gives me D, right? 3 after A is D. That makes sense so far? So 3 after T is W, and 3 after W is Z. And 3 after Z is, of course, as everybody knows, closing curly brace. Everybody knows that, right? That's going to be a bit problematic because if we want to rotate it a bit forward, right, then I need it to go back around. And I can't just simply say mod 26. Why 26? 26 is the number of letters in the alphabet. So it actually becomes a bit tricky to do that, but not too bad. What we need to do is that we have to get it from working in the space of 95 to, what the heck's Z anyway? Or Z. So we want to get out of the range of working from 97 to 122. And rather, we should probably work from 0 to 25, right? Why 0 to 25? That's 1 through 26, but we'd like to start things from 0 in computer science. And it'll make our modular arithmetic easier. So, what we can do is that given a letter, like some kind of letter, let's say our letter is equal to R, okay? The way we can convert that letter is, first off, is that we want, we'll get the value of it is equal to ord of the letter, right? Get the value of the letter. We don't really care what the value is, just that it has a value. But also the thing we're going to do is that we are going to do minus ord of A. Why are we subtracting ord of A from it? By the way, it looks even weirder in Python because I'll literally be, not Python, it looks even weirder in Java because in Java, shell, I would just literally be subtracting, doing something like this, J minus A and get 9. So at least in Python, it makes you spell it out what you're doing here rather than trying to hide it from you. But here, value is ord of letter minus A, right? Letter is whatever the value of letter is, right? The ASCII value of it, minus 97. And as a result, we get 17. How's that significant? Well, if you look at if we were to do this for, well, let's look at what this does for all the letters. So if we did this for A, we get 0. For B, we get 1. For C, we get 2. Right? So let's go ahead and I'm going to spell this out with a for loop. Yep, one more time. For I in range 65 to 126. Actually, let's go from 97 up to, yeah, let's actually, I don't want to memorize what those ASCII values are. Ord of A to up to and including ord of Z. How do I make sure I include it in my for loop? I'll add 1 to it. So here we're just going from A to Z, all the letters from all the values from A to Z. Print I, CHR, I, CHR, I, minus ord of A. So in other words, subtract, oh, actually I don't want to do that. Sorry, just I minus ord of A. And then I plus 1 minus ord of A. That plus 1, not going to really use it anywhere else, but you'll see why I'm going to use it in just a second. Right? So if we look, that doesn't look pretty. So what I'm going to do is I'm going to use another command that I may have used before, but I'll be more explicit about now. Just like there is an end. Notice how I separated all the things I wanted to print out by commas in the print statement? There's a sep command which says this is how I'd like things to be separated by. By default, if you print multiple things out with a print statement and have them separated by commas, it'll just separate them with spaces. But you can define how you want them separated by using the separator operator. Here I'm saying print all these things out, all these arguments out. I'd like them separated by tabs, please. Looks a lot cleaner. So if we look at this chart, A has a value of 97. And if we were to subtract A from it, it has 0. Add 1 to that, you have 1. Now for R, which we were working with, R has a value of 114. If you subtract A from it, it gets us to 17. And the reason I'm adding 1 is because if you look through this, A is the first letter of the alphabet, B is the second, so on and so forth, until R is the 18th letter of the alphabet. So that 17, the significance of that is just 18 minus 1. Instead of it being the letters 1 through 26, of the first through 26th of the alphabet, we're going from the 0th to the 25th. Okay? Why the 0th for 25th? Because it's going to make our life so much easier when we're doing modular arithmetic here. Okay? So that's kind of given us the idea of why we're doing that. So if we go back to value, right, we subtracted A from it. We got 17 because it was the 18th letter of the alphabet, 18 minus 1. Okay? And so if I wanted to encrypt it by, say, 3, and we call what we want to encrypt it by, like by the key. In this case, the key is just a number, 3. The key is different from one thing to another. In Caesarean cipher, the key is the amount you'd like to move it forward. I think actually we want a key of 13 or something like that. So here what we want to do is take say the value is that, take value plus key, and that will give us 30, which is not a valid letter of the alphabet, right? Valid letters of the alphabet have to be from 0 to 25, right? They're the first letter through the 26th letter. So it's asking for the 30th letter of the alphabet, right? I want the letter that's 13 after R. Doesn't exist, right? R is the 18th letter of the alphabet. Adding 13 to that will give us, we'll be asking for the 31st letter of the alphabet. So 17 plus 13, that's why we got 30. So what do I want to do in that case? I'm going to use modular arithmetic. Because what a modular arithmetic also works with is that it will just simply, anything above that value will just simply rotate around. You can think of also, so one way to think of modular arithmetic is like a clock, right? How like 6 hours after 7 o'clock is, well, 8, 9, 10, 11, 12, 1 o'clock. So 6 hours after 12, those are 6 hours after 7 is 1 o'clock. In similar vein, we would rotate this around. So, right? So 13 values, right? Q, so this would be R, 1, S, T, U, V, W, X, Y, Z. So we're up to 8. A, B, C, D, E. What did you do today? Oh, my professor just simply was in front of class yelling about the ABCs or something. So we went all the way up to E, 13 letters, and that rotated us back to 4, right? See that? So modding by 26 allows us, basically says that if it goes over, so when we have something like this, we can say if it goes over 26, start by rotating. If it goes over, then basically start again from the beginning and keep counting until we don't have any amount over. So, right? So we're back to 4. So 4, and then what can we do with that 4? Well, what we can do with that 4, and this is the hardest part of this, I swear. What we can do with that is that we can add the A that we just subtracted out. That will give us 101, 101Z, right? And then CHR that. So these series of steps that are now way too, that basically are making your mind kind of explode are all you need to just convert a letter. But we'll go through it a bit slower, or we'll piece it together now. So the idea here is we want to take these and use Caesar cipher 13. So key is equal to 13. We need the result in ciphertext. It's equal to empty string. For letter in plain text, let's go ahead and say the value of that and value of the letter is equal to the ord of the letter plus minus a right? The encrypted value, or the cipher value, right? So this is what we want when it's encrypted, is value plus key mod 26. So we're adding the key in here, we're rotating it, and if we rotate too far, the mod 26 brings us back to 0 and starts it up again, right? So modular arithmetic brings us around, right? The idea here is basically, okay, if it's 7 o'clock now and I want 7 hours after 7 o'clock, mod 12. By the way, the parentheses here are very important because of order of operations. So 7 hours after 7 o'clock is 2 o'clock, right? What's 15 hours after 7 o'clock? It's 10 o'clock, right? Just simply goes around. So we add value plus key, mod by 26, so that basically repeats, starts over again from 0. And then we need to convert it back to the actual letter. Cipher, I'll call it cipher letter. It's equal to take the cipher value and add ord 26, or not ord 26, ord of A back in, and then turn it into a character. So notice what I did over here. So here, first step, I turn that letter into its value and subtract 8 from it. So it gets so now that's in the range of 0 to 25, which is a range that I can actually work with when I'm doing modular arithmetic. Then what do? I add the key that I want to that value and mod by 26, so that basically, just in case I go over, I'm going to wrap around back to the beginning, right? So if I'm adding 3 letters after Z, I don't go, what in the world is that? I go, oh, 3 letters after Z, that's A, B, C, right? That's how it will work. And then I add the A I subtracted back in and then turn it back into a character, right? Got to add that A back in because I subtracted it out. Otherwise, I'd be printing out gibberish. And then ciphertext is equal to cipher letter plus, or sorry, all I have to do is plus equal cipher letter. And save and run. And pass. Great. So I have the ciphertext value, and and it successfully encrypts it into, let's see what their encryption is, right? It's the string we're converting, by the way, is the quick brown fox jumps over the lazy dog. So print ciphertext to see what we just converted into. Gird, blah, blah, blah. Okay. So wait, how do we know that that works and it's not gibberish? Excellent question. Glad you asked. So the one thing about it being rotating something forward 13 letters, how many letters are in the alphabet? 26. So what happens if I wanted to encrypt this by rotating the letter forward 26? It is a Caesar cipher that does absolutely nothing, right? Asking for letter 26 after brings you back to the beginning, right? A, the letter 26 after A is A, right? If we view it like a clock, right? A, you count off your letters. A, B, C, D, so go around, hit Z again, bam, we're back to A. Okay? So 26 does nothing. So if I move something forward by 13, and then I take that ciphertext and move it forward by 13 again, I get the plain text, right? So here, 13, okay, and then if I take this text over here, paste it into here, right? So here I'm taking my ciphertext as my plain text and running it again, I get my output. Get the quick brown fox jumps over the lazy dog, right? I just moved it forward 13 and then I moved it forward 13 again. So, pretty good indication that this works, I'd say. So let's go ahead and put this to practice. So the problem with the Caesar cipher, as I was mentioning, is there's only 25 possible rotations because the 26th rotation brings you all the way back to A. The 27th rotation is the same as the first rotation, right? Moving forward one letter is moving A to B. Moving forward 27 letters, 26 of them bring you back to A, and one more after that brings you to B, right? Makes sense? That's why this is what modular arithmetic is. So let's try to unscramble this. So what we're going to do is we're going to steal this over here, and we are going to try to decrypt the ciphertext. Okay? We're going to decrypt the ciphertext by encrypting it again, rotating it forward again. I mean, the other thing I could do is that I can try to figure it out by, well, if you encrypted it by moving it forward by 3, then all I have to do is subtract 3. How does that work in Python, by the way? Just in case. Because it works differently, I think, in Java. So like if I did what? If I did 13 minus 16, which isn't a problem in itself, but if I were to mod that by 26, what do I get? I get 23, which is helpful. -3, right? So what is 13 minus 16? 13 minus 16 is -3, right? So if we're starting from 0 and counting backwards, 25, 24, 23. Because we're in a modulo 26 space. Right? Right? So, why should I drop it? So, A, B, C, D, E, right? Z, Y, X, A, sorry, Z, Y, X, W, right? So here, 0, 1, 2, 3, 4, 25, 24, 23, 22. If we were to rotate forward, right, with A plus 3 gives us D, which is 3. Right here, if I'm saying that I want to subtract 3, if I want to take -3 mod 26, let's just do -3 mod 26, it gives me 23 because start from 0, 1, 2, 3, negative goes backwards in that modulo space. Not going to have to remember this for any exam, by the way. Negative modulo, especially since it works differently in Python. The answer there, sorry, in Java, the answer is -3 because that's the remainder. Python says, well, actually, it should be this, but whatever. Okay. Suffice to say, I can just simply, there's the ciphertext. So let's modify this code a bit. We want to try 25 different keys. So for key in range 1 through 26. So we want to try those different keys. Yep, we're going to be indenting a lot of this. So we've got our key. Plain text is equal to blah. So we're starting from this, and we want to decrypt out what it is. Oops. Yeah, I have to indent this in here. Plain text is equal to blank. 4-letter in the ciphertext, right? Since I'm going from the ciphertext to the plain text, even if you don't understand the numbers over here, right? For encrypting something, from turning something from a message that I understand to a message I can't understand, I was adding. So that makes sense to do the reverse. I need to just subtract the key rather than add the key, right? So I'll do that here. All I did was change this to minus. It will still be 0 to 26 because of the way Python works. So we'll take the value. Let's change the value names. Plain value is equal to value minus key. Plain letter is equal to the plain value plus the ORed. All I'm doing is changing cipher to letter and changing that minus key, that plus key to minus key. Plain letter, plain text, and then what I'll do is I'll print out plain text and the key. I'll do the key, print out whatever the key was and the plain text. So the reason I put it in this, I have this nested for loop here, is that I'm trying it for all the different keys. So first I'm going to try it for key 1. Then I'm going to try it for key 2. Then key 3. Then key 4. Then key 5. Then key 6. Does that make sense? You seem a bit confused. Yes, it will be reset each loop, but I'm printing them out, so I'll be able to look at them. Because I'm trying to figure out, because I don't know, I know this is Caesar cipher. I don't know which Caesar cipher it used, right? So did it use a rotation 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13? Not sure which one. So I'm going to try them all. And let's see. And look for one that looks reasonably like English. I'm going to do that sep tab again. Is there one that looks relatively like English in here? 17? Minnesota United Football Club. A very important message, apparently. So 17, by rotating it backwards 17, we got our answer. So the original shift was 17. All right, so it's not very secure, by the way, to do it like that, because you get enough slave scientists working on the problem parallel, they can decrypt about anything. In fact, even when we go up to the Veneer cipher, which Veneer cipher, which was the height of security in Civil War and World War II, was like, here's a reproduction of the Confederacy cipher disk that they used. The idea here is that basically take attack at dawn, and then your keyword is lemon. So you spell out lemon as long as your message is. So here it's attack at dawn is 12 letters long, so they spell out lemon, lemon, le, right? Because that's just lemon twice, and then le. You make it as long as you need here. And then what you're doing is that you've got 5 separate Caesar ciphers going on at the same time. All the letters that are rotated by L, all these letters, this first letter, the 6th letter, and the 11th letter, all rotated by L. whatever the value of L is. The second letter, the 7th letter, and the 12th letter are all rotated by E, whatever the value E is, being its numerical value, and so on and so forth. So attack at dawn with the key lemon becomes this. And trying to decrypt it with the Caesar cipher just doesn't work because you actually have to use 5 different Caesar ciphers at once. Still solvable, by the way, using different things, using cryptanalysis. The way you would try to figure out these things is using cryptanalysis. So frequency analysis of letters, every language has a fingerprint that you can't erase even if you substitute all the letters. Like, for instance, we know that E is the most common letter in the English alphabet, right? Other languages have different fingerprints like that. But you can kind of figure it out. So, like, here, if the key is ABCD, crypto is short for cryptography. Here, notice we've got a repeat, right? So here, the ciphertext for the for our Veneer cipher is this. It repeats a bunch. Crypto is short for cryptography. You take the plain text, you encrypt it by the key, and you notice just by happenstance, by coincidence, that crypto translates to the same thing each time. It's just coincidence. So that's one way that you can use it, repeats like that. If you know, for instance, that basically you are, so this was a very, very common thing in World War II, using what's called a crib, which is that basically you know that the Nazis are going to sign off their messages Heil Hitler. Or you might know a specific one like that. So that makes it pretty easy to crack. So if you know what the answer is, that makes it or part of the answer is, it makes it pretty easy to work backwards. Another thing that was also easy is if you've got a small outpost in basically northern Africa that's doing nothing. Nothing goes on there, nothing there, but he's got to send in daily reports, and his message is, date, blah, 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 nothing to report here, signed, this person. You know it's the same message every single day, so you've got an answer that you can work from. So cryptanalysis is nifty like that. But anyway, suffice to say, Caesar cipher is not really that good, and you could just solve it with pencil and paper. Veneer ciphers are possible to solve if you've got enough practice at it. However, we decide to instead just mix up the alphabet instead. It becomes a lot more interesting. So rather than mixing up the answer, right, we can say A becomes Z, but B will be P, and C will be L, and like all sorts of things like that. Oh, and we're gonna make D's the ampersand because I can, right? We do that. So that scrambling becomes our key. And then if you were to scramble up the alphabet, then you have this many different keys. 26 to the 26th power, I believe. Oh, no. 26 factorial, my bad. Yeah, 26 factorial. So 26 times 25 times 24 times 23 times 23. So yeah. Right. So it's a very big number. But the idea here is like, for our previous alphabet, right, this was our input, this was our output. This is what we would get with route 13. But here, the idea here is that let's take this key, and what we can do is that we can translate our ins and out. We don't have to, it has to be A through Z up on the top, but it can be whatever the heck I want on the bottom, so long as I don't have any repeats over here, right? So, suppose, right, rather than doing modular, and this will be easier, rather than doing modular arithmetic, we're just going to just say, here's our input, here's our key. Give me the ciphertext. And that actually will work out pretty well. So, notice that over here that we're saying, by the way, we can change anything we want. Notice we're going to change all the spaces into Qs, right? The space is lined up above the Q, and the E is lined up, and we're going to turn all the E's into spaces. That's actually that's actually pretty smart, turning your E's into spaces, because spaces are actually the most common thing in the alphabet, in the English language. The most common character, not the most common letter. Every single word has a space after it. So we'll take our alphabet and apply our key to it and use it, and so it will look something like this. So for letter, this will look even easier. You'll be wondering, why did Professor Rosen do what he was doing earlier when he could have done this? Because it's always nice to show you the hard way to do it first so you can appreciate the easy way. So for letter, assuming I can spell, in the plain text, right? First, I'm going to figure out what letter of the alphabet it is by saying, by getting index is equal, or rather, I is equal to alphabet. Okay, this variable over here, alphabet dot index of that letter. So what does index do? It gives me the index of the letter. So if I pass in D, it's going to return 3, which is the index D appears in letter. Sorry, D appears in alphabet. That makes sense to everybody? Index is a fairly straightforward function. Get the index of D. Or rather, get the index of D. Okay, it's 3. And I'll store it. How do I figure out what D goes to? Well, we've got our key here. So ciphertext is just equal to key and use that index, right? Get the index of D and then grab the corresponding index from key. So we'll get 3, and then we'll get index 3 from, so this value will return 3. So let's go and look at this for of. So it will return whatever index O is at, sort in I, and then it'll say get the ith thing in key, which will be the thing that's right below here in S. So if we store it and run it, let's see, fail, actual value, expected F equal to, why are you expecting F? Write a program that will encrypt the plain text. Store your, right, so why does it expect F? O goes to S. So actual value is F. Oh, my bad. Plus equals. There we go. So the way this works is that we use the index function and this alphabet variable, right? We pass in a letter. Let's go ahead and see how it works a bit more since Python 3. Let's go ahead and steal this. Okay, alphabet dot index of A returns 0. Alphabet of index 5 returns, alphabet of index E returns 4, right? So I'm asking, where's this letter in the string alphabet? Z, that's at index 25. Space, 26. Exclamation point isn't anywhere. Make sense what the index function does? So let's go ahead and grab key now. So now, right, what I can do is that if I find an E in alphabet, I can grab its index 4 and then ask key 4. What's at index 4 in key? And it will say space 0, 1, 2, 3, 4. And so if I see an E, what's going to happen is that I'll look up in key I'll look up in key the space and replace it with a space, and that's what happens. So our ciphertext becomes this. So of shoes and ships and sealing wax, of cabbages and kings, becomes that. If I wanted to decrypt a ciphertext, by the way, it works pretty much the exact same way, just in reverse. For letter in ciphertext is equal value is equal, so the index I want is equal to ciphertext is equal to key dot index, because we're going from the key to the alphabet now. Key dot index of the letter. So get the letter in here, find what index it appears in here, and then plain text is equal to nothing. Plain text dot append, nope, sorry. Plain text plus equals alphabet. I. And that's let's go ahead and see what we did. I passed the exam, but I have no idea what it is. So plain text. The sun was shining on the sea, shining with all his might. So that's basically the basis for encryption here. Now, the question is, since we've got the remaining time, is like, so how good does this work? And the answer is, it's okay, but it still is susceptible to what we call frequency analysis. Right? Frequency analysis looks like this. The relative frequencies of letters in the English language, basically if you count up all the letters that we would get in that, like, for instance, in this, we'd notice that E is 4. So we'd notice that of those characters, the spaces appear around 12% of the time in a long enough message. In a long enough message, we'd get kind of this fingerprint over here, saying that this character appears 12% of the time and this one appears 8% of the time. And so from there we can figure out E and A. We can figure out our vowels. And each language has a different, so here, Itoan is basically the way to remember the most, or the most frequent letters in the English language. But like these are like if you were playing Hangman, which guesses should you make first? Start with E, then T, then A. Those are the most letters if you want. Also, if you have an N in the second to last position, an I and a G are probably good guesses, because that means you've got an ing word. So that can be broken still. Most really good encryption these days uses public-private key encryption, which basically lets generate random numbers using a seed, essentially, of a specific type. There's a lot of good ones, a lot of different encryption different ways to encrypt a message, but there's only one unbreakable way, only one, or one that cannot be broken by cryptanalysis, because everything can be broken. There is no cryptographic defense against a baseball bat to your kneecaps repeatedly. You will give up the secret key at that point. There is no cryptographic defense against a subpoena. Hand over your key or you go into jail. Those kind of things. There are no So basically, when we talk about cryptanalysis, cryptography has a hard job because it has to deal with the fact that we're making all these schemes for making codes or for making ciphers. By the way, you want and we're talking about spying, so it is a bit of bloody business, which means that basically we do, things like using force to get what you need is something you think about when you're doing cryptanalysis. Also, as a result, if you're an encryption guy and you're making encryption algorithms, typically the way we do encryption algorithms these days is that we subject them to peer review. We say, okay, like RSA is like one of the most popular encryption schemes out there. Cryptography, the Rivest Shamir Edelman is one of the first public key crypto systems, where the encryption key is public and is different from the decryption key, which is kept private. So everybody knows how to decrypt something, but not necessarily know how to decrypt it. It's actually amazingly useful. It's really clever. It's difficult. It's possible to decrypt it, but it takes forever. Like, everybody is going to be dead by the time you decrypt it, and all their children, all their children's children, and in fact, the world's probably going to be gone and eaten up by the sun by the time you decrypt a message that's been encrypted like this. It's the number of things you have to brute force and work through, and that's great. But the idea here is that, like, we want this to be published so that basically that somebody could possibly find a flaw in it so we could correct it if there's a flaw, right? We don't want to just blindly use it. We want to put it out for peer review and see it. But the other thing is that when you were, say you were a king back in the feudal times, it was very good to be the king. Your word was law. And you wanted to build yourself a castle, and of course, part of the issue is the reason you build castles is that you're going to get sieged at one point. And you're thinking, maybe I need a secret escape tunnel out of my castle. So you have the architect build a secret escape tunnel out there. Now it's a secret escape tunnel. So what do you have to do to make sure that it remains secret? That's right, you kill the architect, and now it is secret. Then the necessary amount of people that need to be... So a secret is secret only if one person knows about it. Any more than that, and it starts becoming much less of a weaker secret. So cryptographers have it in their best interests, and computer scientists have it in their best interest for that not to be the case for them. But that's going away from the whole thing over there. So the only way that can't be broken using cryptanalysis is a one-time pad, as we call it. Here is one format of a one-time pad that was used by the NSA. So here's our pad, and basically here's the use. And basically what you do is that you have this pad of randomly generated letters, okay? And what you would do is that you would start on your and your partner would have the same exact pad, okay, of these randomly generated letters. And what you would do is that you would go, okay, well, if I'm saying attack at dawn, A and L, so here A, and I would like L, so that's going to be an O. F, go over here. So I want a T, actually, and an F would be B. Right, and so basically you're doing a Caesar cipher for every single letter in the alphabet without any pattern in there, okay? There's no repeating pattern in there. It's all completely random. But the only way your partner can reconstruct it is if they have the exact same random pad. So, and then you start this, and suppose your message is 15 letters long. Next message, you're going to start from here. You're never going to reuse any bit of this. Once it's done, it's done. Now again, it cannot be beaten by cryptanalysis. What it can be beaten is somebody coming in and stealing your one-time pad or something like that. Or if you send the one-time pad to Agent Joe, malicious Agent Mallory comes in, offs Agent Joe, and pretends to be Joe while you're communicating with him. So that kind of stuff. So cryptography is actually really fun to think about those kind of things. But so it's really all, so again, we are going to be working with text, and this is actually a really good way to be dealing with text. Now, using this, you're probably never going to be doing this in our class. This was more of a, let's show you how this works in the ORD and CHR function work, okay? This, on the other hand, using the index and using this, really useful. So tomorrow we're going to start on file reading. And with that, we're going to use that to learn about slicing strings more. We're going to learn more about splitting and joining, because we're reading files, and files mean text.